Hello everyone, good evening. I'm Anish Becker, PhD candidate from Aerospace Engineering at Bengaluru. Welcome to this week's live session for the NPTEL course Computational Mathematics with SageMath. As is the custom each week, we'll be going through a set of problems which will further elucidate the concepts that have been taught in the previous week. So in this week, that is week 10, we learned about how we use how different methods to solve say ODEs, including numerical methods, Laplace transform, as well as making use of the slope fields and so on and so forth. With that in mind, we'll be beginning this week's session. So, example one, the population growth of Bengal tigers in a conservation park having has carrying capacity 100 and requires minimum of 10 to survive. Population model is given by dp by dt is equal to r into p into 1 minus p by k into 1 minus t by p, where t is the minimum threshold and k is the maximum capacity. Okay, so with this in mind, we have been also told that initial rate of growth is 1% and initial population is 15. Now we have been asked to draw slope field for this given differential equation. So we'll first check the help on slope field function. So slope field function, it's a function used to basically, it plots the slope field of f of x comma y. So here we have f of p comma t, and at each point, it at each x I comma y, it will plot a line with slope given by f of x y. So whatever function we give, so suppose at p equal to p naught and t equal to t naught, we have the point p naught comma t naught. And if we have provided this as the function, dp by dt is equal to rp, this whole expression as the function, then this expression will be evaluated to find the slope of the line, and a small line will be plotted passing through p0 t0 and with this slope. With that basic explanation out of the way, we'll be plotting slope for p of t. So firstly, as is a good practice, we'll be specifying the variables p and t. Constants are also specified, following which we define the function f of p comma t. So this is nothing but the derivative of p with respect to t, and we use this to plot the slope field. So slope field will plot for points for p going from 10 to 100 and t going from 0 to 200. It will plot uh, lines with these sort of slopes. Lines with slopes given by f of p comma t. Running this function, I see the slope field like this. Okay, so here there is uniform larger slope, and then at the edges of 110 population, the slope is almost zero, which is also what we expect from this function 1 minus p by k and 1 minus t by p terms. To help visualize the slopes better, we'll be plotting streamlines. So same thing, but now we'll be plotting an entire streamline. So the streamline, as you can see, goes through like this. So each of these streamlines represent a possible solution for dp by dt. Our challenge is to find a particular solution. Our challenge is to find a particular solution wherein p at t equal to 0, p should be equal to 15. So t equals 0 and t equals 15. Somewhere here lies our solution. Okay, around this point. So maybe this line is our solution. Let's see. To obtain the exact solution, we'll be using the DSolve. This is the differential equation solver inbuilt function in Sage, wherein a differential equation, differential variable, dependent variable, sorry, initial conditions and so on are specified, and it can solve either a first or a second order linear or including both IVP and BVP cases, initial value and boundary value problems. Now we define now we define the differential equation, but to do so we first specify p as a function of the variable t, which is what we have also defined earlier. And then we write differential equation of p comma t. dp by dt is nothing but f of p comma t, which is what we have already specified here, f of p comma t. With this in mind, with this definition, we ask do solve to solve this differential equation for the dependent variable p. Okay, so we see an equation which has log of p and a constant c coming up. To do away with the constant, we'll be providing initial condition t equal to 0, t equals 15. This gives us solution of the again initial value problem, and then I'll be just multiplying by a factor of 9 by 1000 across this entire expression and then simplifying it to obtain the value of p. So p of t ends up looking like this sort of complicated equation, and if I just obtain the right hand side of this equation, this is what it looks like. Now suppose I have to plot this equation, so I think here I had limited t to 20 itself, I think. Yeah, t was limited to 20, so I will be plotting for the same range itself. T, uh, t limited to 20 and plot this. Okay, there's not much change here, but if I plot it for say slowly increasing, if I give it increase it one order more, it should saturate, right? So it starts off very slowly, then increases, and then eventually saturates. So maybe one thing I could do is see how the streamline plots look. And this is okay. This is continuing from here, right? Had we specified P and T. So this is how the streamline field looks like. And if I increase it even further to 1000, essentially everything reaches 1000 in itself. I think I should flip around the x and y axis to show this better. Okay, so uh, this is P and this is T, and now you can see that our solution should started off somewhere here, and then it converged after around 800 or so from this plot, and from this plot also it comes out to be similar. Okay, so like the whole idea here was to show that how say a slope field plot or a streamline plot can help us infer or rather visualize possible solutions to the derivative function, and this is how we have done it and obtained solution for our specific initial value problem. Okay, any doubts here? If not, I'll move on to the next problem. Example 2 asks us to solve the initial value problem. Dy by dx equal to 1 by 1 plus y upon 1 plus x square, and y of 2 equals minus 2. We have to plot both the slope field as well as the solution. So slope field we have plotted x-axis, y-axis going from minus 4 to 4, and I could actually restrict x to only 2 to 4. Okay, I'll just leave it for now. We are first specifying variables x, y, then we are defining the function expression f of x, y. Next, we will be plotting P1, which includes slope field given by the function f of x, y for x and y going from -4 to +4, both of them. If I run this cell, this is how the slope field looks like. If I restrict, okay, uh, so x equals 2 is here and y equals -2. So y equals -2 is somewhere here. Okay. Now we'll be solving this expression. First specify again the variable x for y as a function of x. Then the differential equation. If y comma x is equaling f of xy, then we solve it using solve for the dependent variable y. And then we print the solution. The solution looks something like this. And if I specify these conditions, x equal to 0 and y equals -2, my solution of the initial value problem looks like 1 minus e raised to minus r10 of x. If I have to plot this for say x going from say 2 to 4, because that is the case I have above, I can see that this is how it looks like. Y of 2 is -2. I made a mistake. Right, so this is how it looks like. A gently downward sloping line. Okay, if I increase its range even more, seems to be saturating after some point. Suppose I increase y from -3 to 3 and x going from 2 to 100. So this is where we start off, and this is how the line saturates. So the solution also follows the same nature and same values. Okay, any doubts with this one so far? If not, we'll continue with the third example. Example number 3. Solve the second order ODE, which is given as y double dash minus 7y dash equals 4x into e raised to 7x, with the initial condition y at 0 being -1 and y dash at 0 being +1. So how do we do this? First, specify variable x, then specify y as a function of variable x. Next, write down the differential equation as d is diff y comma x2, which is second derivative of y with respect to x, minus 7y dash minus 4x into e raised to 7x. This whole thing going to 0 is my differential equation, right? So it matches with what we have. Next, we will solve this using the solve command, provided differential equation, dependent variable y, and initial condition is y of 0, x at x equal to 0, y equals -1, whereas y dash equals +1. If I plot the solution, so it looks like increases very rapidly. So that is why I put on a smaller value, so 0.5. So it also, you can also see that if you are interested, you can find a root for this expression. You can see visually that it will lie somewhere between zero point 0.2 and 0.3. Okay, so this is how we will solve a second order ODE. Any doubts here? Alright, then we'll move to the next example. Example 4. Find the exact solution to the following equation and use that to find an exact value for y of 2 for the initial value problem. Compare the error in Euler's method and modified Euler's method with step size 0.1. So dy by dx equals 2x 1 minus y with y of 0 going to 2. Right. So solve this. We want to solve this equation. So the first thing we'll be doing is get the exact solution. To do so, we define x as variable x, y as the function y of variable x. Differential equation is dy by dx minus 2x into 1 minus y going to 0. If I print the differential equation, this is what we see. So this matches with what we have. Next, uh, sorry. We'll be solving this using the esolve function, wherein we have a differential equation, dependent variable y, and at x equal to 0, y equals to as my initial condition. If I run this cell and print out the exact solution, this is what I see. Sorry, excuse me. Okay, so this is what we have, and to find exact value for y of 2, we'll be basically evaluating the function solution exact at the value x equaling to, and from this we just print out our exact solution. So the exact solution is 1.018, so on. Okay, if I want to say plot this function, I could solve exact x going from 0 to say 2 and show even fixed size. This is what we see. Okay. Next, we'll be using Euler's method. So, uh, in Euler's method, we define the function f x0 y0 as my initial condition, step size h, and x1 as the final point till where I want to evaluate this. Okay, so first we define our number of points as x1 minus x0 by h. So total difference upon step size gives us number of steps, and I basically assign xv and yv as my variable x's first initially to my initial condition. I create a solution array in which I have already fed my initial value x0 comma y0. Uh, Next we have for I in the range of 1 to n plus 1. So this will cover x going from x0 plus h all the way till x1. So we define x variable as x0 plus hi and uh, y variable plus h into f of x variable comma y variable, which is nothing but this second statement is nothing but uh, the estimated value of y is the previous at the next step is the previous step uh, is the value of our previous step plus step size h times the slope. So very basic, like the simplest approximation possible, and then to the solution array we append xy comma yv. Now I'll be using this method below. Again, first specify variables x comma y and then specify the function f of x comma y, which is 2x into 1 minus y. Next, we will be running Euler's method with step size 0.1 initial x0, y0 are 0 and 2 respectively, step size 0.1, and final value x1 is 2. Now I'll be running the Euler method algorithm. Sorry, function. So you can see that x increases in steps of 0.1, and y also changes values. Based on this, you can see that the Euler method, uh, the value of y using the Euler method with this particular step size for this function, for this form of differential equation and the provided initial conditions x0, y0, that turns out to be 1.07007. So I'll just be printing this value using Euler method, and the error turns out to be 0.01. Okay, so this is how this looks like. Next, we'll be using modified Euler method. In the modified Euler method, we have the function f, x0, y0 as my initial condition, again h as my step size, and x1 as my final point where I want to evaluate y of x. Next, again the same function, except the uh, except the way your new y value is calculated. So everything is x0, xv is nothing but x0 plus ih, and yv is nothing but h plus 2 h by 2 times the function value evaluated at x comma y, and the different slope evaluated at x plus h comma y plus h times x plus h. So this is the current slope. This is the slope at estimated forward value, which is vx plus y h and vy plus h into f of vx vy. With this in mind, the modified Euler method algorithm is complete, and now I'll be using it below. You can see that I still have everything same: variable xy, f of xy, x0, y0, s0 and 2 respectively, step size as 0.1, my final value is 2, and then I'll be running the modified Euler. I see my value to be 1.013. Okay, so seems like this. If I run this, my error value comes out to be, sorry, my exact solution I know is, I've evaluated, I think somewhere here, 1.018. This is 1.007, and this one is 1.013. So my error is 0.0049. If I plot both the solutions, okay, so you can see that somewhere here a swap between modified Euler and Euler takes place for this particular function. Maybe if we play around with different, we'll see a slightly different nature. But the key idea is that as you go more and more into x along the x-axis, you will see that modified Euler becomes closer and closer to your uh, exact analytical solution as compared with, say, the vanilla Euler, or like the standard Euler method. Okay, so with this we complete both uh, like the Euler and the modified Euler methods. Any doubts here? Okay. Next up we have example number 5, which says convert the second order ODE given below into a system of ODEs and hence solve it using DE solve systems. Verify your solution by solving the original ODE using DE solve. So the ODE that we have given is 4y double dash plus 4y dash plus 17y equaling 0, and the initial condition being y of 0 is minus 1 and y dash of 0 equals to. First, I'll solve this as a pair of ODEs using the solve system, but we'll just quickly have a look into what the solve system is. So it's basically takes a list of ODEs and list of dependent variables, initial conditions if there are any, initial values for the independent variable as well as the dependent variable. So both of them have to be specified. Okay. Next step, we'll be trying to solve this as a system of ODEs. First, let us specify the variable. And here I'm writing. Okay, I think I made a mistake. This should be x. X. I'm first specifying variable x. Next, I'm writing y as the function y of x. Then I'm defining another function y1 of x, and now I'm specifying my system of ODEs. So to do so, I have first written out my first differential equation, which is dy by dx equaling y1, and my second differential equation is dy1 by dx, which is nothing but y double dash of x is 4y 4y dash plus 17y divided by minus 4. So this whole thing brought to right hand side, and this 4 also brought here. Okay, this gives me my second differential equation. If I print this out, dy by dx is y1, and then dy1 by dx, which is nothing but y double dash, is given here. Now I will be solving this using the solve systems, where I am specifying my differential equations d1, d2, my dependent variables y and y1, and my initial condition is x equal to 0 gives me y as minus 1 and y dash or y1 as 2. Solving this, I see my solution looks something like this. Next, I'll be solving this whole thing as a second order ODE. So instead of uh, same process, variable x, y as a function of x, and then differential equation directly contains second derivative of y with respect to x, as well as first derivative of y with respect to x, and so on. Then we solve it using dsolve, specify the variable to be y and initial conditions as given here. Now if I show solution 2, this is what it looks like. Minus 1 by 4, 4 cos 2x, minus 3 sin 2x, equals to minus half x. So this matches with this. If I just compare this, they both turn out to be the same. Whether we use a system of ODEs or we use a single second order ODE, our solution should be same, which is what we see here. Next, example number 6. Here we use the Runge-Kutta method with step size h equal to 0.1 to find approximate values of y plus 1 whole square y dash is equal to 2x plus 3. Y of 1 is 4 at x equals to. Again, Runge-Kutta method, brief recap of the fourth order Runge-Kutta method is we find out 4 slopes k1, k2, k3, k4, and then weigh them unequally with the step size h to obtain new estimate of y. So I will be first defining the Runge-Kutta method fourth order as so it takes f x0 y0 h x1 next and as my number of steps. Sol is my solution array, and as spec as sorry as written we specified at the beginning what it looks like. So with this in mind, uh, for all the steps for I going from in 1 to n, so range I 1 to n plus 1, we see this k1, k2, k3, k4 calculated as shown here in the formula. and then we evaluate the new value of x and new value of y and append it to my solution array. Very simple, straightforward procedure, nothing too extravagant, and simply this will give me a solution array of x comma y. Right. So if I run this cell, this is what the function runs without any uh, syntax error at least. Next, we specify the variables x comma y. We define the differential function f of xy y dash is equal to f of xy as 2x plus 3 upon 1 plus y whole square. I show f. This is what my derivative function looks like. Next, if I specify the initial conditions x0, y0 is 1, 1, 4, h is 0.1, my final value is 2, and then I run the Runge-Kutta fourth order method and save it to the variable t. T is now, or rather the array t, which is now used to uh, mark up this, sorry, fill out this table xi comma y. So 1 4 going to 2 4.229. If I plot the solution, this is how my approximate solution looks like. Okay, suppose I decrease the step size further to say 0.05, 0.025. Solution would look something like this. Okay, so pretty reliable method, no change in this case. So this is what we have. Any doubts with this Rangigutta method or any of the problems that we have discussed so far? Example number 7. Use the Rangigutta method with step size h equal to 0.1 to find approximate values of the solution y dash plus x square y equaling sine of x of y of 1 equals pi. Oh, this is at x equal to 2. Okay, so we have to solve this. First, we specify the variables x and y. Next, we write down the function f of xy, which is nothing but y dash. So it will be sine of xy minus x square y. This is how it looks like. No easy way to solve this analytically. Maybe if you know, you could let others as well know how to do so. So to get the approximate solution, we'll be using Runge-Kutta method. Fourth order, we have already developed the function above. Specify the initial value x0 as 1 and y0 as pi. Specify the step size. Write x1 as my final value of x, and then I evaluate this. Then I will be evaluating this my table. T is equal to RK4. Now, provided this function f of x, x0, y0, h and x1, I'll print out this in the form of table. X I y I looks like this. 1 pi and then going to 2 0.05. I think I could also plot the solution in a similar manner as to here. If I print this is how the solution looks like. If I play around with the step size even more, I'll just let the, if I reprint the solution, how it looks like. Oh, I think I went a little too fine with this. Yeah, this is how it looks like. So in this way, we can solve a seemingly difficult problem to do analytically using uh, Runge-Kutta method. Okay, straightforward. Any doubts with this one or the previous one? Okay, it seems this one is also clear. There are no doubts. We'll move on to the next example. Example number 8. Use the Rangekutta method uh, with step sizes h equal to 0 0.1, 0 0.05, and 0.025 to find approximate values of the solution of the initial value problem. So the differential equation is given here, and we have to find the value at x equal to 1. Okay, so variable x comma y, again we specify it, good practice. Next we write down f of xy, which is minus of 2x plus cos of x whole divided by 3y square plus 4y. We'll be doing show f. This is my dy by dx. Next, I specify my x0, y0, which is my initial condition, my step size, x1 and t1. Next, I'm writing, printing the solution in the form of table, which is what we have done every time. This is how it looks like. Solution T1 gives me a value of 0.659. Next, I repeat the same process, but only change the step size, 0.05. I again run the Rangekutta method and store it in the uh, table T2 or solution array T2 rather, which I display in the form of table here. Okay, so there is some change in like after 6 digit also, 65995764, 65995704. So like 1 in a million, or even I think a tenth of that, 10 raised to minus 7. That there itself a change is coming. And if I run it again for a smaller step size, 0.025, store it in the array T3 and then display it in the form of a table 5768. So here again there is some change coming, 5764 or 576. So very small errors, relatively speaking, in between each of these approximate solutions. So if I plot the solution, I expect them to be coincident. So what we see here. Okay, all right. If I, if, yeah, I think this covers this particular problem. Any doubts with this example? Lotka-Volterra population model. We have seen like a two species model. Here we have been asked to look at a three species model. So the equations are given here: dx by dt, dy by dt, and dz by dt as functions of x, y, z, where x, y, and z represent the lowest level, mid level, and the top level species. An example of such ecosystems could be like mouse, snake oil, and so on. It's required that all the constants a to g, so 7 constants are there in total. All the constants are positive. This is what we need out of it. Okay, next we'll be defining the first up. We'll be defining the Lotka-Volterra three species function, which basically returns us the first derivative of the state capital X equaling small x y z, and this is basically dx by dt. So this function gives me rate of change of state of the system, like overall system. Now I define a Rangekutta fourth order method function, but this one specifically targeted to a system of ODs. So instead of one ODE, we have like three ODs. So there are minor modifications specifically around how x0 is instead of a scalar now becoming an array, and then accordingly we have calculating k1, k2, k3, k4 again as arrays. So which gives us basically xk plus 1 to be the next value of the state of the system. Again, that thing will again be an array. Okay. Next, I'm defining my parameters. Everything is specified to point 1, so 7 parameters. I'm defining my function f using the lambda function that we have already seen, I think, in the second class, wherein I assign f of xt to be Lotka Volterra 3 species of x comma params. My initial population of present predators is given here, and okay, so this is what I have. Suppose I play with this even more, 100 and just and I have an initial time, end time, and a step size, right? Now I'll be calling my RK4 system function to calculate x comma t. And if I plot this function, this is how it looks like. Okay, so this is a much more steeper function. Suppose I assign the values to. Yeah. So one interesting thing that we see here is there is a sort of cyclic nature to the set of values and parameters that we have chosen. If I play around with the values even more, I'll be changing the cyclic nature even more. So suppose I specify everything as 10, 10, 10. Okay, so right, so here for this case, it seems like the number of cycles have increased, or the period has decreased rather for the system. One more thing we could play with, suppose like the parameter A, which specifies the natural growth of species of the lowest level species. So if I double this, what I see is an interesting behavior wherein the lowest level species keeps on increasing and the apex predator follows it, but the mid-level species doesn't go beyond a certain value. So if I decrease the amount of time for which I'm plotting this, right? So this mid-level species goes to almost to zero. So right, and it's not zero exactly, but I think I can show that it might be better. Starting off at and to restrict, why is it? So let's see, can I np dot log x1. Right, so you can see that in the log plot, I think this is clear. You can see this. So it means that it's getting to a very small value, but it's not going to zero. And I think one more thing I could do is I'll plot the actual values and then I'll also plot the log values. The log will give us a better nature of, better understanding of the nature, removing out the magnitudes, rather large magnitudes. Alright, so this is what it looks like for t is equal to 100. Yeah, t equal to 100, you can see that this is increasing, and uh, the logarithmic plot also shows that the log value is also increasing almost in a straight line. So you can see two interesting observations here. Firstly, the period size that comes seems to be shrinking for all the species. Secondly, the slope of the log line, like for both, rather the average slope of the log plot seems to be constant, which means that beyond a certain point, you may be able to approximate the lowest level as well as the apex predators population as something of the form e raised to a1t and e raised to a2, e raised to at for both of them, or e raised to kt rather, not a, because we already. Okay, if I go back again to my chosen set of population, chosen value of parameters. So it's almost going to mid-level species population is almost going to zero at some points, which is also visible. One of the drawbacks of this model is like because it's a continuous model, right? Dx, dy, dz. You cannot like even if it's a population for a population model, you have to necessarily restrict it to integer values, which is not something that happens. That is also actually what allows the model to recover the mid-level species population. Otherwise, beyond the point, say beyond this point, if we do not take integers for y of t, if we rather take integer for y of t, then we'll be basically having a case where the mid-level species entirely vanishes. So one of the ways we could justify using such a continuous model for a discrete system is if suppose the time scales are large enough wherein you're not interested in like very exact values, but you want to look at a close approximation of the system. In that case, you do have that here. Okay, and you can also see that how the and log and the normal plots again they have to have the same period width. This is what we also see here. Okay, I think this could be explored even more after the session. I'll be uploading the notebook as well. So if you want, you can play around. Lot of parameters. Like there are I think around 10 parameters, 7 and 2 here, 3 here. So and play around with this a bit. One more case that could be of interest is suppose you have very large uh, population, a small mid-level population, and even smaller apex predator. What happens in this case? Oh, this has exploded. Is a log? I need to reduce this 110 one. Still facing it seems bit of a problem in this one. Not sure why. Right now it's solved. Okay, so yeah, this is how it looks like. And suppose I'm just curious. No top level product. Does this work? Or what I'll do is reduce the top level predator to a very small value, non-zero value. Seems like the top apex predator pretty quickly catches up as the lowest level prey, after which mid-level species catches up, following which apex predator also catches up. So we again get back to the periodic nature of population. So population cycles rather. Okay, a lot happening. A lot can happen provided you play around with the parameters even more, or if you want to increase it to say like a four species population, so on and so forth, you could do that. We'll move on to the next example. If there are any doubts here, you may ask them now. Otherwise, I can move on to the next example. Number 10. Explore the SI and SIR epidemic models. So, what is the SI epidemic model? SI refers to susceptibility and infected. So, you have S susceptible people, I infected people, and beta into delta t being that a random infective person infects a random susceptible person. So the rate of change of so the increase in the number of infected people is I of t plus delta t is I of t plus beta delta t s of t into I of t, which gives me di by dt is beta s I, and we also have this this is very simplified model wherein we assume a constant population n. So whoever is, so there, if you have a fixed population capital N, you will either have people who are infected already denoted by I, or you will have people who are susceptible to the infection, which is S. So S plus I gives N. And then di by dt, rate of increase of infected, is given as beta Ni 1 minus I by N. So, which is basically a logistic equation with beta n as the growth rate, and we expect di by dt to go to 0 as I will tend to n. So, as t goes to infinity, entire population should become infected. So, we define SI epidemic as, again, like we follow the same process that we have done here. We define capital X as my state, but herein, because S plus I is equals n, I only have one variable in my state, which is infected. So dx by dt is beta into n into infected minus 1 minus infected by n. So this gives me rate of change of state of my, sorry, rate of, yeah, derivative of the state of my system. I define beta as a very small value and my n to be 10,000. These are basically my params to be fed into the SI epidemic function. I use again the lambda function to define f of capital X comma t is SI epidemic of capital X comma params. So capital X again only contains the infected population. So X of 0, initial state is I0. So there was only one infected person at t equals 0. And as we march along up to t equal to 100 in time step of 0.1, I see my capital X comma t as follows. So you can see my number of infected people basically increases and keeps on increasing. If I do a log plot for this one also, so you can see that in the log plot, it initially starts off with a constant line. So when I is very small, 1 minus I by n is approximately 1, and therefore di by dt is grow. Di by I can be, capital I can be approximately written as exponent of beta and t. So this is how it looks like for the lower time. For the, as the time increases, you can see that our equation sort of slows. Sorry, rate of growth of the infected people sort of slows down, which is what we expect. I increase time for the, let's say, 2000. I think this will take a bit of a time. Let's see. You can see that this is how the infected looks like. And if I look at the log plot, same. Initially some curve, some slope, constant slope, then slowly the slope reduces and then it finally becomes zero after a sufficiently long. So in the SI epidemic model, one thing to note is that everyone becomes infected provided sufficient time. So you can see right away that this is not in line with what we see with our eyes, where people do recover and so on. So to get the dynamics into the model, we use the SIR epidemic model, which is basically my susceptible, infected, and recovered population. Okay. Again, same assumptions. No birth, no death. That holds true because, like an epidemic, basically dynamics of the epidemic is much faster than dynamics of birth and death. And then we have the system of equations defined as ds by dt is minus beta is by n, di by dt is beta is by n. You can recognize this beta is by n from like the above equation that we have. And then there is a uh, recovery factor given by gamma I minus gamma I. So the number of infected goes down by gamma I. And then my dr by dt is my rate of change of rate of increase of my recovered population from the total population, and I basically use this about three equations to uh, write down the rate of change of system state capital X. So beta, gamma, n are my parameters, and dx by dt is rate of change of my system. Three variables, so three differential equations specified in this 3 by 1 array. Next, I specify my beta gamma parameters. You can see that the way that I have specified, gamma is far larger than beta, which basically tells me that the population recovers faster than it gets infected. And again, the same process. Initially, there are 100 infected out of 1000. Remaining are susceptible, so 900 are susceptible, and none of them have recovered. If I run the system and plot the value, see that something is happening here. If I if I print only the infected one and the recovered one, you can see that the amount of infected is slowly coming down, whereas the amount of recovered is increasing. You can also see an interesting thing that the amount of recovered exceeds the amount of that recovered is because the number of people getting infected can keep on sort of increasing with time based on how large the susceptible population is. You will end up with a case where you have more number of people who are infected than who were initially infected. So initially only 100 were infected, maybe somewhere around 150, 140, 150 end up being totally infected, and that is what we see in the recovered plot. If I only plot the susceptible one, should have something around 850, which is what we see. Provided large number of time, sufficiently large amount of time, we see that the susceptible infected and recovered rates basically curves basically plateau out. Again, a problem with this model, which is similar to the above Caldera three species model, is that this is a differential model modeling a so trying to replace a discrete system, or rather model a discrete system using continuous functions. So you have a case where the infected population isn't like going to zero entirely, rather it just sticks in, becomes a very small value. So if I were to plot that in log fashion, what do I see? np.log. np.log is basically my natural algorithm, so log to the base e. So the infected is straight going down. Susceptible and recovered have increased and plateaued at some points. If suppose I play around with the rates and let my recovery be same as my infected, I can see that my number of infected doesn't vanish here. Maybe it may require much longer time. This is what the log plot tells me, that the amount of susceptible is uh, slowly becoming, so it's also decreasing, which means that almost everyone at some point has gotten infected. If I further flip this script around and decrease recovery even further, which would be a deadly case, you can see that the number of susceptible keeps on decreasing, which means that everyone at some point is likely to get infected. if I increase the time to sufficiently large value, or if I rather I'll increase the time to large value. It will take a moment to solve. Right, so you can see that there was a point where number of infected were quite high. After a while, even that starts dropping. This number of recovered keeps on increasing. Okay, all right. So this is the SI and SIR models. Any doubt with this one? Again, you can see in the log plot that the recovered is e raised to minus 2. So again, not an integer, but I think this model can still act as a good approximation, so to speak, for the discrete system. So if you have like very large population, right? Suppose n is say 100,000 or 1,000,000, point two, point two, same recovery and rates, and 1,000 of those were infected. Okay, I'll let this run. You could play around with the rest of the parameters. This notebook will be again uploaded in the drive. So yeah, any doubts with this question so far? Okay, if this is clear, we'll move on to the next problem. We wish to solve the initial value problem, y double dash plus y equals sine of 2t, with y equal to 0 and y dash equaling 0, using the Laplace transform step by step. And we'll be verifying our answer both using DESolve and DESolve Laplace. So, as is the custom, a good habit is to first specify my variables involved. So, st and capital Y. Capital Y is basically for the Laplace Y. Next, the small y is function of t. Y is equal to y of t, and my differential equation is what I have here written down in Sage. So y the pseudo square y by dou t square equals sine of 2t. Next, I take Laplace function, Laplace transform of this differential equation. So s square Laplace of y of t, ts minus s into y of 0 minus y dash of 0 and so on. Right? If I just print this equation, this is how it looks like. Okay. Next, Laplace transform of the differential equation is converted. Like I, I write LTD is my Laplace transform of the differential equation and write it down as a string. This is how it looks like. Now I want to replace my y of 0 and y dash of 0 in this equation. To do so, I'll be replacing the parts of the string with first replacing the Laplace y of t in the string with the variable y, and next replacing y of 0 and y dash of 0 with the values 2, 1, which is what I have been provided with. So if I print it, my first replacement is capital Y, Laplace of yt. My next replacement is y of 0 will go to 2. My third replacement is y dash of 0 should go to 1. So this is how my equation looks like. Next, I use Sage to evaluate the string of equation into an actual expression. This is what I get as my this is what I get as my actual expression. We have assigned the string s to the variable s and string y to the capital Y to the variable y, which are already specified. Next, I solve this equation for the variable capital Y, and my solution looks like this. So, cubic polynomial by quartic polynomial. I can simplify this using partial fraction, and then I basically take inverse Laplace of this equation. Okay, so my solution ends up looking like root twice of cos of t minus 1/3 sine of 2t plus 5/3 sine of t. And my inbuilt solver looks like using my inbuilt solver, Laplace rather inbuilt solver, I get my solution again to be same. And finally using my inbuilt ODE solver, I again get the same function. Okay, so all three methods give me the same value. Any doubts with this one? Okay, the next example, example 13, solve the system of equation x double dash plus 2x minus y equal to 0, y double dash minus x plus 2y equal to 0 with the initial condition x at 0, y of 0 and x dash of 0 and y dash of 0. We want to solve this using Laplace transform. X double dash, y double dash are derivatives with respect to time, so second derivative. To call the inbuilt ODE solver, which is the easiest method, first we specify my variables s and t. Next, I also specify my functions x and y as functions of t. I write my first differential equation dE1 as x double dash plus 2x minus y, and my second differential equation as, sorry, I'll just add this second show. My second differential equation is y double dash minus x plus 2y. Then I'll solve this system using solve system. This is how it looks. Next, will be using the Laplace method. Same process. Specify variables capital X, capital Y as the Laplace transform of x of t and y of t respectively. Next, we calculate the Laplace transform of the differential equation and first differential equation. And for it, we replace the particular terms in the strings with capital X, capital Y, x of 0 and first derivative of x. This is how the first transformed equation looks like, first differential equation looks like after transformation. Same process we repeat for the second differential equation. Now we solve this too using simply the solve function. So you have two variables, capital X, capital Y, and two equations. So solve function should give me like solution of linear problem. This is how it looks like, and if I print this solutions, the inverse form, this is how they end up looking like. Cos of root 3t plus 3 cos of t and minus cos of root 3t plus 3 cos of t. So this is what my x and y look like. Okay. Next we have, if we want to compare this with my above equations, my x of t is given here. d0x and d0y are both 0, so there is no sine t term, sine of root 3 as well as sine theta. And x0 is 4, y0 is 2, so 4 minus 2 is 2, so 2 by 2 is 1, so you have got cos of root 3t, and the second term is 4 plus 2, which is 6 by 2, 3. So you should have cos of root 3t plus 3 cos of t as x. Cos of root 3t plus 3 cos of t. Right, same thing you could do for, if you put x0, y0 in the y1, you will get the same answer as below. So in both the inbuilt function as well as our function, we get the same value. Any doubts with this one apart from the initial? Okay, final problem for the day. X double dash plus 8x dash plus 16x is equal to 16 sine of 40 with x of 0 specified and x dash of 0. We wish to solve this using Laplace transform. Everything that we have learned so far, straightforward, will apply. X, t and x as my variable, small x of t as my function, d as my differential equation in x of t. You can see that this matches with what we have been provided. Next we do Laplace transform of the differential equation. Replace the capital X variable, replace the initial value x of 0 and replace the first derivative x dash of 0. Once we have this, we have an equation which looks like this, and we solve this using solve function. Now we only use the right hand side part as excess, convert into partial fractions, and finally get the inverse Laplace solution. So t raised to minus 40 minus half cos of 40. Same process if we run through the inbuilt ODE solver. So D solve, differential equation solve for the differential equation for the dependent variable x with these initial conditions. This is what we end up with. So in both cases, for the second order linear order ODE, we end up with, which is an initial value problem, we end up with the same solution irrespective of which method we choose to use. Okay, any doubts with this one? If not, then I think we'll call it a day.